Testing. Testing. Maybe we wait a few more minutes. The people will come along. In the meantime, anyone have some quick questions? Sure. Okay, maybe let's get started. Okay, good morning, everyone. I have finished marking all your quiz, but I cannot give you back today yet because there's one more person haven't took it, and she'll took it this Friday, so I will return it next week. Okay. I think the average is about 17.5. I think it's quite high, and about 28 of you get full marks. So I guess quiz 3 will be harder. Otherwise, I think everyone will get 100 in this GE course. Yeah. Yeah. Mm, you guys want some proof question? Okay, just want to hear some feedback for you. I'll try. I'll see. I won't make it too hard, but definitely should be harder a bit. Okay. Otherwise, everyone will get 100 marks in this GE course. Any quick questions before we go into today's content? Okay, if not, let us recall what we did yesterday. Okay, let's do the map up. So in this week's story, we start with a vector space. Okay. Vector space contain two operations, vector addition and scalar multiplication. Okay, include. Okay. So yesterday or the day before, we found that we can find a set of bases in vector space. If we can find a finitely many, we call it a finite dimensional vector space. So this is what we call the finite dimensional vector space. So what's the use of bases? So the use of bases is to express every vectors in your vector space uniquely. You have a unique way to describe your vectors in terms of the linear combination of your basis vectors. Okay, and yesterday we also proved that if you found any other bases, they will all have the same number of elements inside. Okay, if one basis have n elements, then all the other bases will also have n elements. So this is what we call the invariant. This is an invariant of your vector space. Invariant is something that doesn't change. Okay, so you take the dimension and then you get the n out. So this n is a natural number. In case you don't know what natural number is, so you can include like 0, 1, 2, 3, 4, 5, and so on. So you count the number of the basis vector. So this is an invariant. And we also established that if it is a finite dimensional vector space, we can also take a special linear transformation. Okay, what's the linear transformation? It's the coordinate vector. Okay, the special vector that describe the vectors in your vector space. And this thing is a vector in Rn. Okay, so we established that there's an isomorphism between these two spaces. So it's the same. If you want to study finite dimensional vector space, it's the same as studying Rn, right? We turn the question in the set of polynomials into Rn, where we do the row reducing using the coordinate vectors. Remember the example we did yesterday? Okay. So also from Rn, we also can take dimension of Rn, right? Dimension of Rn, okay, which is also n. So in both cases, we get n. change n, we get n. So what is Rn? Rn, what's the basis in Rn? You want to know what's the basis in Rn? What's the basis in Rn? What's the basis in Rn? Remember? One can recall. What's the basis in Rn? E1, E2. Okay, so the standard basis E1, E2, R2. Okay, so these are the 1 and the I spot. Okay, we call the standard basis. So you can see that both bases has n element. Okay, so the isomorphism is 1 to 1 between this basis element. Okay, there are n basis element in the vector space, finite dimensional vector space. There's also n elements in the. Yeah. Okay. Yeah. Okay. So this is the invariant. We got the dimension. So the bottom point is the dimension is dimension of a vector space is an invariant vector space. Okay, so you won't get the 2 dimension out of one vector space. One vector space with 1 dimension, where you count the number of vectors in your basis. Okay, because exactly we have this theorem here. Every basis has exactly n elements. So if you change your basis, you will still have n elements. Change another basis, you still have the same number of elements. You won't increase or decrease. Okay, so today we will finish up 4.5. Is it 6 or 5? 5. 4.5. How to find a basis. And then we will continue with change of basis. Let's say you have 2 bases, how you change between bases. So although the not right 4.7, right, is a 4.6 in the 6th edition textbook. Okay, if you wonder. And then after that, we will go into a little bit talking about the eigenvalues and eigenvectors. Hopefully we'll stop there. So today we will address the question of how to find how to find basis of a vector space in general. Okay, so how to find? So how to find something that spans the vector space, and how to find that they are linearly independent. Okay. So actually we have encountered it once. Okay, if you can recall that we have encountered one theorem called the spanning set theorem. Okay, so what's spanning set theorem about? So let's say you already found some vectors and then consider all the linear combination. So that means you consider the span of a few vectors, okay, call it H in this case. Then some subset of H is a basis of H given that H is non-zero. Okay, if it is 0, then there's no basis you can find. Okay, 0 vector. Everything is linearly dependent on 0. So one example you should keep on your mind is, for example, we have a span of 0, 1, 1, 0, 1, 1. Okay. So there are various ways to see why you have extra linearly dependent vectors here, right? So if you consider the matrix formed by this column, okay, you'll see that it is a 2 times 3 matrix. Okay, the most pivot column you can get is 2. So you must have at least one. Okay, let me go out and then join again. Okay, let me move this. Okay, so it becomes smaller. I move away. Okay. Okay. Yeah, somewhere. Okay. So can you all see? So for example, look at the span of these 3 vectors here. Okay. There are various ways to see why these 3 are linearly dependent on each other. One way to see it is if you consider the matrix formed by the column, the matrix whose column formed by these vectors, right? It forms a 2 by 3 matrix. So in a 2 by 3 matrix, you can at most get 2 pivot. Okay. So you must have at least one free variable. So the solution to the homogeneous system is non-trivial. Okay. So you can actually so, so you can see that in other way is can I write down or are you guys okay? Do you want me to write down or you guys okay? Okay. So the other way is you can directly see that 1 is equal to 0 1 plus 1 0. Okay. So you could just remove it because you already write 1 as a span of the other. So what you can do is really throw away 1 inside of spanning set. And what is this? This is really R2. Actually, it's R2. Okay. It's a basis for R2, where you can see it's span at linearly independent. Okay, so this is a spanning set theorem. What's spanning set theorem talking about? So if you have a span of linearly independent vectors, you can throw enough such that you reach a linearly independent set so that you form a basis. Okay. Okay, next is this theorem here. But let's say you instead of starting with spanning set, you start with linearly independent set. Okay. So let's start with an H. Is a subspace of a finite dimensional vector space, meaning this vector space have a set of bases, and then you can count the bases, it's finitely many. Any linearly independent set in H can be expanded, if necessary, to a basis for H. Also, H is finite dimensional, and dimension of H is less than equal to n. So we won't prove this. This is just some I would say common sense. Okay. Let me give you an example why I say it's a common sense. So, for example, let's say you want to find basis of R3. Okay. So you want to find basis of R3. Okay. Uh, can you give your favorite R3 basis vector? What's your favorite one? Give me a favorite. Favorite, huh? What? Yeah, say. Yeah. Any favorite one? Favorite vector in algebra? E1, E2, okay. Sure. So let's start with E1. Okay. So E1 is what? 1, 0, 0. Okay. So 1, 0, 0. And maybe you pick an extra 1, 0, 1, 0. Okay. So the question is the span of these two equal to R3? Yes or no? Why not? For example, yeah. Yeah, for example, 0, 0, 1, 0, 0, 1 is not equal to C1 times 1, 0, 0 plus C2 times 0, 1, 0. Okay, right. How to see this? How to see this? So you should use what you have learned now. Okay, how you see this? This is a vector equation. Okay, so in vector equation, what can you do? You form an augmented matrix, and you see that this is inconsistent. Okay, right. So what everything you learn now, right, actually built toward this vector space. Okay? Vector space is really what we want to study. What you learn in chapter 1 is a tool we use to explain, to calculate. Okay, it's just a tool. But what we really want to study is this kind of thing. Okay, so now you see that it doesn't span. Okay, so it doesn't span. So can you see if these two are linearly independent or not? Are they linearly independent? Okay, they are linearly independent, right? Why? Because it is a pivot column for the pivot column. There are pivot column in every column, right? So it's 1 to 1. So if you solve, so if you change the matrix, change to solve the homogeneous equation, it is the trivial solution, right? Okay, this is everything you have learned. So the theorem saying if it is not span, expand it. Okay. So what basis uh, what vector you want to add into the span? So what vector you want to add into the span? Hmm. What vector you want to add into the span? Huh? 114. Okay. Add 114 inside the span. Okay. So let's check this then. So first of all, um, let's check. So we want to check whether these three vector is actually a basis of Rn or not. How about okay. Okay. So let's ask the question again. Have we got the basis vector for R3 now? Okay. So let's check span. Okay. So we want to write any vector in R3. Let's write x bar such that x bar is equal to C times 1, 0, 0 plus C2 times 0, 1, 0 plus C3 times 1, 1, 4. Right. Okay. So the easiest thing you do is you can, since this is easy, right? So one way to do, you can do by inspection. Okay. Just find C1, C2, C3 and then test it. Or the standard way is the augmented matrix. Augmented matrix. Okay. So what you do is you set up your momentum matrix 1, 0, 0, 0, 1, 0, 1, 1, 4, and then you want to find the coefficient, the solution to x or the b. Okay, maybe we change to b so that you will be more related to the matrix equation. So let's call it b1, b2, b3. Okay, so we go back to first week. So how to solve this? Is this a row reduced echelon form yet? No, right? Okay, so let's do some simple row reduced trick. And then we can do row 2 minus row 3, row 1 minus row 3. This one, I forget to change. Huh? Yeah, okay. 1, 0, 0, 0, 1, 0, 0, 0. And we get b1 minus b3 over 4, b2 minus b3 over 4, and b3 over 4. Okay, so this will be our C1, C2, and C3. So C1 is b1 minus b3 over 4, and C2 is b2 minus b3 over 4, and seems like a bit too small, is it? C3 equals to b3 over 4. Let me pick the back one. Okay, so in this case, let's put it back here, put it back here. So here is b1, b3 minus 4 times 0, 0 plus C2 is b2 minus b3 over 4. Okay, I'm a bit too excited here because before that, you have to make sure that this is actually a consistent system for B. Okay, it's a consistent system because in a square matrix, you have every row you got a pivot. Okay, yeah. So if every row have a pivot, it's equivalent to every column have a pivot. Okay, so if it is equivalent to every row have a pivot, then it's also said that these three vectors are linearly independent. So you together you solve both questions. Okay, so okay, let me write down. Since every row of the matrix has a pivot, then the column vector of the matrix span R3. Okay, and then in a square matrix, it is equivalent to every column of the matrix has a pivot, which means the column vectors are column vectors are linearly independent. Yeah. Okay, so they are linearly independent, so they form a basis. So they form a basis. So it's okay. All right. So last time I also tells you that R3 is a span of E1, E2, and E3. Okay. Does this contradict each other? No. Okay. We can have different basis vector to represent a vector space. Okay. But the number of the vectors doesn't change. If one have 3, the other must have 3 as well. Okay, so this is the invariant you get from vector space. So you got 3 basis vector here. Here must also have 3. So you can stop now. So you've already found all the linearly independent one, and then expand. Okay. So this is the theorem here. So as long as you check they are independent and then up to the dimension you have before, then it's okay. So this is um, a valid basis for R3. Okay. Okay, next. Okay, next we come back to this theorem again. Okay, so the basis theorem. So there are two ways to get the basis. So any linearly independent set of n vectors is a basis. Okay, just now we see it somehow. Any set of n vectors in V that span V is a basis. Okay, let me get rid of this. Okay. So last time we used a tricky way. We used contradiction to prove this. Okay. Today we were using what we have learned, the spanning set theorem, and what we have established just now to see this theorem again. Okay. So let me make it. So let me label it. Okay. Is this too thin or you want to fat? You want this fat? You want one or this one? First one or second one? Ah, first one is okay. Okay. Because yeah, see if you can see it. Okay. So let's look at this one. So let's look at first one. So any linear independent set of n vectors in V is a basis in V. Okay. So what we can use is we just use this theorem here. So let me crop it if I see if I can. So we can use this theorem here. Okay. Okay. So let's start with any linearly independent set of n vectors. Okay. The theorem says that any linearly independent set H can be expanded to a basis of H. Okay. Let's say you already have linearly independent n vectors and your dimension is n. If you try and put more in, what happens? What will happen? What will happen? Okay, in fact, by this theorem here, right? Okay, in fact, by this theorem here, you no need to expand already. Okay, so even linearly, cancel. Okay, but a bit small. Yeah, that's why I was thinking. Okay, never mind. I just use this one. Okay, let me make it big. Okay. Okay. So given a linearly independent set of n vectors. Okay. So how do you show that it is a basis? So by theorem before, okay, you can expand it, but since the dimension of V is n, okay, it is orthogonal automatically a basis for V. Okay, so that's mean if you happen to know reason you can. Okay, if you happen to know the dimension of your vector space, okay, if you happen to know the dimension of your vector space is n, and then you try to find the basis, you pick linearly independent vectors, okay, one by one. If you already pick n of them, okay, then you can stop. You don't need to check span. You just pick n of them, then you can stop. Okay, so this is the first part. The second part is any set of n vectors in V that span V is a basis of V. Okay. So what does this mean? So this means so we have a spanning set theorem. So let me move the spanning set theorem here. Okay. This and then change it to okay. So if you change it, if you start with spanning set theorem, you have a span of n. So let's start with what we have. So given set of n vectors in V, okay. So the spanning set theorem said then the subset of H is a basis of H. Okay. So a subset of it is a basis of V. But you know that the dimension of V is n. Okay. So it couldn't be less than n. So it is again automatically. Okay, before that, maybe I will talk a little bit again. So given a set, let me move this guy. Okay, so by spanning set theorem, okay, what do we have? By spanning set theorem, a subset of it is a basis of V. Okay. However, however, it cannot be a proper subset. Okay. Otherwise, the dimension will be less than n. However, it cannot. I think a bit still small. It cannot be. It cannot be a proper set since otherwise the dimension will be less than n. Since otherwise the dimension B is less than, is strictly less than n. So it is again automatically a basis for B. Okay, so it might seem like quite natural what you say, or you don't know what I say. Okay, but I urge you to compare to what happened last time. Remember in Rn, I also proved this kind of theorem. Try to compare both. Okay, the first one is I start with n of them, I add one more, and then I get contradiction. But for this one, is I start with n, and then I say I can stop. You know, it's like, so the two flavor is, one is I go from above to below, from greater than n plus 1 to n. The other is I go from below n up to n. Okay, you get what I mean? So there are two ways There are two ways to get to n, right? Okay. There are two ways to get to n. One is going from large to small. One is going from small to large. Okay. So this is today. So that one is last time. Okay. Try to compare the two proofs. Okay. See what's happening inside the proof. Okay. There's nothing to prove here, but it's just a process like the algorithm. Okay. There's nothing to prove here, but just a process. All right. If that's it, then we will finish. We will stop at the basis here and then continue. Okay, change of basis. Okay. Just now we already saw that we already produced two bases for R3. Okay. Let's see what we can do when we have a change of basis. Okay, let's look at this example here first. So consider you have two bases, okay, B1 and B2. We didn't tell you what is the base, what is B1, B2, but doesn't matter. What matter is how you relate these two bases. Okay, so since C is a basis, right? Okay, B, the bases in B also live in the same vector space. So you must be able to express B1, B2 in terms of C1, C2. Okay, so here is the relationship. If X is a vectors in R2, okay, so now we live in R2, such that the coordinate vector of B is X1, is 3, 1. Find the coordinate vector of C. Okay, so let's see what information we have now. Okay, so what does the coordinate vector tell us? What does the coordinate vector tell us? What's the definition of coordinate vectors? Can anyone recall? Anyone recall that? Anyone recall? Coordinate vector is the coefficient in the linear combination of the basis vector. Okay. So here we have two bases here. So with respect to B or with respect to C? B. Okay. So it tells us that X is a linear combination of vectors in B. Okay. So what's the coefficient in front? What's the coefficient in front? 3 and 1. Okay. So this is what the coordinate vectors tell us. So yeah, okay. So now you want to find in terms of C. Okay. So can you go from B to C or not? How? Using the information given here. Okay. So it says that 3 times for C1 plus C2 plus 1 times minus 6 C1 plus 6 C2. Okay. And then what is this? This is 12 C1 plus 3 times C2 plus, minus, let's expand it, minus 1 C1 plus C2. Okay. Yeah, so if I really pedantic about it, about vector space, I can put something like this. Okay, so what do we get? We get, you see what we get? What's the coefficient for C1? Is 6, and then C2 is 4. Okay, so now you use the definition of coordinate vector again, okay, where you get 6 and 4 for the coordinate vector with respect to C. Okay. So this C actually you can draw like, okay, so for this B and C, right, you can draw like this one and this one. It's a script B and script C. Okay, so actually you don't realize you realize here what happening here is actually a matrix multiplication. It's actually a matrix multiplication. Can you see what matrix you should multiply to get 3, 1, 2, 6, 4? Can you guess what is this? There's a matrix multiplication happening here. Can you see it or not? And let you spend some time if you can see it. You are actually doing matrix multiplication. Can you guess? It's just 2 by 2. Can you guess what's the entry? So the hint is try to think about how you multiply in matrix, right? How you get this number. So how you get this 6 from here. So how you put the number here. Anyone idea? Anyone got any idea? Huh? What number? 2. Mean 2. And then 0. And then no, cannot. You can. But seems like there's nothing to do with the number here, right? I mean, you use the number here to make this computation here into a matrix multiplication. Yeah. Use the number here that appears here. Yeah, of course, this matrix gets you this vector, but it seems nothing to do with the question. Anyone? Any idea? Four, 1 minus 6, 1. Okay. So what is 4, 1? It's the coefficient when you express B in terms of C. Okay. So minus 6, 1 is the coefficient of B2 when you write it as a linear combination of C1, C2. Okay. So what is this matrix? This matrix is really a okay, so what's this matrix? This matrix is really B1 in terms of C and then B2 in terms of C. Okay, and then you will get what you want. And then what let me change into algebra. So let me change to algebra. So here is x b equals to x. Okay. So if you have a question, say you want to get from coordinate vector expressed in B to coordinate expressed in C, what you need to do is express the vector in B in terms of C, and then take the matrix, multiply on the coordinate vectors relative to B. And then you will get coordinate vector relative to C. Okay. Yeah. Is it okay? Can you remember the process? So to get the coordinate vector in B to coordinate vector in C, you need to find how you express the vector in your the basis vector in your B in terms of C, then you can move everything to C. It makes sense? So yeah. Okay. So you can think of it like this one is a B to C, and then this one is a B to C. So what you get is B to C. Okay. Makes sense? Yeah. Okay. Okay. Okay, so wait, is it okay? Okay. Yeah. So if you want to go to B to C, then you need to express your vectors, basis vector in C, and then multiply on the coordinate vector in B, then you will get coordinate vector in C. Okay. So the theorem is like this. So in general, if you start with n vectors, just now we only have 2. Then there exists a unique matrix, okay, which is we found just now. We call it PB to C. So let's rename this matrix as PB to C, okay, such that when you multiply the coordinate vector B, you will get the coordinate vector on C. Okay, this is unique. And this theorem tells you how to get it. You just need to express everything in B in terms of C, in terms of basis in C, so that you can change to C. And what's more is actually these columns are linearly, these columns, yeah, these columns are linearly independent, okay, because they started from basis, so they are linearly independent. So it is invertible. It is a square. It is square matrix. It is invertible. So if it is invertible, then that again, not that this is an n by n matrix, okay? Because you are going from n, you need to express n things in terms of n things. So it's an n by n matrix. So they are linearly independent because uh, they started as a basis element. Then getting smaller and smaller. Okay, so PB to C is an n by n matrix, okay? And then these columns are linearly independent because they started as a basis element. So inverse exists, okay? You can find the inverse. So what can you do with inverse? You can multiply inverse on both sides, and then you get actually the inverse of PB to C is PC to B, okay? Because let you see this thing. So let me show you. So, so let me write it here. So, okay. So what do we have just now? We have a change of basis from B to C. When you multiply the coordinate vector in B, you get coordinate vector in C. Okay. And we say that the columns of PCB is linearly independent. And PBC is a n by n matrix. Okay. Why? Because 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 you because we express n vectors in the linear because we express the n vectors in B in terms of the linear combination of n vectors in C. Okay. Hence, hence PBC is is invertible. Okay. So in particular, the inverse exists. Is it okay? Linearly independent on square matrix imply you have an inverse. Because if it is linearly independent, then you have pivot on every column. If you have pivot in every column, it's the same as pivot in every row for square matrix. So it is row equivalent to identity matrix. So it is invertible. Okay. Yeah. So if it is invertible, Then you can find the base inverse. So let's call it B to C inverse. Okay, let us multiply on both sides. On both sides. What do we get on the left-hand side? The matrix can cancel, right? Because it's the inverse of each other. So we get the identity on one side. So which is just the coordinate vector of B, right? These two cancel. These two, wait, let me, so these two multiply to identity. Okay? It's okay. Okay, yeah, okay. So what we got is another matrix that multiply on the coordinate vector of C, and then we get coordinate vector on of B. Okay? Right. Okay, so inverse of P, why I changed my arrow here? B to C, okay, is the matrix that when you fit in coordinate vector of C, you get back B. So in fact, by definition, not by definition, in fact, you should check this is really the change of matrix, change of coordinate matrix from C to B. So in fact, you really bring the inverse into this arrow. The arrow really change. You swap the arrow. Okay. So in fact, the inverse of a change of matrix, change of coordinate matrix is just swapping the arrow. Okay. Instead of swapping the arrow, I swap the content here. Okay, so to keep this arrow consistent. Okay, really inverse of a change of base, change of coordinate basis matrix, you just change the arrow. Okay. Okay, nothing special. Okay, but this actually gives a new way to look at matrix equation, really. Okay, let's say question here. Let's say we take one of the bases as our standard basis. Okay, let's put B standard. Okay, which is the E1 .En. Okay, so what is BX? Okay. B standard. Okay. What is this doing actually? Okay. So does anyone know what does this part simplify to? Coordinate vector for the vector in the term of a standard basis. What's this part here? This is really the vector itself. Right? Remember? So not remember, but I'm not sure you observe or not. So let's say we have x equals to 3, 2, 2. Okay. So what's the coordinate vector for 3, 2, 2 in the standard basis? Yeah. So what's the coefficient in front the standard basis? What's the coefficient in front of the standard basis? Or 3, 2, 2. Huh? It's just 3, 2, 2. Okay. So a normal vector, right? For normal vector in a standard basis, the vector and the coordinate vector coincide. Actually, they are the same. Okay, that's why we call the basis standard basis. Yeah, so it's a kind of standard. Okay, so it is equal to the 3, 2. Okay. Okay, so why I'm doing this? Because in your uh, you will see, okay, because in the first week we are focused on solving this kind of matrix equation, right? Okay, so let's say this is invertible. Okay, sorry. Let's say we restrict. Okay, in the first week, A can be arbitrary n by n matrix. Okay, let's say we restrict our matrix to n by n matrix, n by n matrix. Okay, and it is invertible. Okay. Then it is really just a change of coordinate basis. Multiply the solution. Okay, multiply the solution where you get B. Quite. Yeah. So if you restrict the case of matrix to the square matrix, okay, when it is invertible, what you are really solving is you find your B in another basis. Okay. Yeah, this is just what I want to tell you. Yeah. So how to say? So every time you want to find a solution, actually the solution is just a different way to express uh, the B in a different basis. Yeah, yeah. A bit weird, but yeah. What? Yeah, seriously. Yeah, see. You see, you have this X, right? Through this PBX, okay, okay, okay. Let me make it more apparent to you. Okay, let me make it more apparent. Okay, so let's say we inverse it. Okay, so we inverse it. So let us inverse it. So we change the direction of the arrow, making it be B standard to B times X. Okay. So what you really do is you want to solve for the solution. Actually, the solution is what you have for this vectors here in a different basis. In the same word, but expressed in different basis. Okay. Yeah, this is just what I want to say. Any question? Why someone look confused? Why someone look confused? Repeat. Okay, repeat again. Okay. Okay, let's repeat again. Okay. So let's say okay, let's repeat again. So we have two bases here. Okay. So we start with two bases. First one is a different basis to Rn. Okay, let me split. Let me state very clearly in the Rn form. So let's have two different bases, right? Okay. Instead of two arbitrary bases, one is arbitrary, the other one is standard basis. Okay. Standard basis is what we understand about vector space. It is exactly how we express the vectors. Okay, right? When the vectors coincide with the coordinate vectors. This part, okay? Okay, this is a normal vector space, normal basis. Then we can see that from this change of basis matrix equation here, we can see that if we multiply the chain of bases from B to B standard, multiply on the coordinate vector of x in terms of B, then we will get x back. Okay. Similarly, because this is invertible, we can move this vector, this matrix to the other side by multiplying the inverse, or we change the arrow. Okay. So this says that we can get x in terms of B, okay, the coordinate of vectors x in terms of B by just multiplying the change of basis from standard basis to B on the vectors. And then I bring out this question here is when every time we solve, so this one is a restriction, okay, we restricted case, okay. Every time we solve the matrix equation, right, we solve AX equal to B. Okay, AX equal to B. We want to find X. Okay, let's say A is an n by n matrix. Okay, we change our A to square matrix, and then also it is invertible. Okay, so normally you can use augmented matrix, or you can also use, I hope some of you already start using something like x hat equal to a minus b bar. Okay, you can use this to find your x. But what are you doing really is just making your b, okay, making your b written in terms of different bases. The coordinate that express your b in the different bases. So I will say express your b in a different basis is the solution you want to get. Can I understand? Can I understand? Any question? Or any question? Yeah, any question? Yeah. Any question? Maybe we'll get one question before we break. Get one question before we break. What I try to think is you want to find the solution to ax equal to b, right? Okay. So you think that maybe this solution have nothing to do with b. Actually, is b in another form. This is what I'm trying to say. Is it? At the start, you might think that x and b is a different entities. Okay, there's nothing to do with each other. But if a is invertible, then there's something, b is just b in a different form. Okay. So you solve yourself. I think Chinese has a phrase, right? Is it most of you Chinese here? I think only one Talia. Is Talia here? Oh, Talia is here. Are you Indonesian? Okay. Indonesian Chinese? Oh, Indonesian. Can you understand Chinese? Yeah, a little bit. Okay. So that's what I think. So I come back to one thing, one philosophy in Chinese. So we say like 解铃还须系铃. Okay. Okay. Yeah. Okay. Okay. Let's stop here and then take a break until 10:18. We'll come back again. Continue.
有一个小
那你
在刚上课讲的，
哦，刚上课，
这一块
嗯
就是说，
你说你
就是 the some subspace of H is a basis of H。我认为就是说，是不是在这个 H 里边有一个，比如说 VM，VM
嗯
它是跟这些线性相关的，所以说就可以把这个 VM 去掉，所以说就是 some subset of H，
对对对，
是这个意思吗？
是这个意思，是这个意思，对，去掉。但是我是说你不能够再去了，如果你再去的话，你的 dimension 就变少。
啥？
你再去掉的话，你的 dimension 就变小。
但是那个也该去掉了，就是就这个 H 里边全是线性不相关，就是线性
也是，
无关的。
但是这个情况是我们不需要讨论它到底是 不 independent 或不 independent，我就可以知道它可以 form basis，这是这个 theorem 的重点。我只要查一个东西就够，就是需要检查一个东西就行。对，
检查一个
就是 either 这全部都 span，或者这全部都 linearly independent，我只要检查一个就够了，我不用检查两个。
全 span 和全里面
但是这个前提是我要知道那个 space 的 dimension 先。
base 的。对，比如说如果说它现在是那个呃，它就有那这个是 Rn 的一个 subspace H
是 Rn 的一个 subset 啊，对
如果说去掉一个线性相关的，
对，
那么它还是 R，就不是，
就不是，
就不是。
就不是，
再想想，上个厕所
就不是，就不是，对，就不是，
一个很奇怪的小问题。然后一个向量，它在这个标准的这个 t，它是23，后随便写了一个这个 base，随便写了一个 basis，然后如果按道理说，如果说我想表示一个从这个空间到这个空间的线性变换，它的矩阵可以直接写成这个。
等一下，等一下在干嘛？对对，你在干嘛？你有 basis，然后你有这一个，然后你这个干嘛？
这个就表示这个空间
你
到这个空间的变化。
可以，
是，
是没有错。
然后，但是如果直接把这个东西乘上23，
所以 OK，我知道了。
表示出来的就不是。
OK，等一下，
是我们想找的。
等一下，你等一下先，等一下，所以这一个是从，喂，这个是从，嗯、从 B 去 C 去这个去这个 standard
去 stand，
对啊，这是这个方向，你要这个方向，
为什么是
因为这里面的东西是 B 在 B standard 里啊，B 在 B standard，B 呀对，B1在 B standard，B2在 B standard，对吧？对吗？所以这个方向是一样的。
所以
嗯，
假如果我想找它在 base B，我得承认这个矩阵的幂。
对对。但是你取了过来过后，它也只是一个 coordinate vector，所以你要看原本的 coordinate vector，你就要看它的那个 linear combination，对吗？
有点
对吗？很多步骤，
有点反直觉的感觉，就是
反直觉。
对，因为
再说一次，
就是
为什么？哪里反直觉？哪里？
这个是从 B 到 standard
啊，对，哎，不，啊，对，因为你看你在干嘛？你在把 B 里面的东西写成 B center 里面的东西，所以你才能够把所有 B 里面的东西再把它写成 B center，可以明白？
啊。
啊，嗯，OK。Hello. Okay, let's come back. So I will pass down the attendance list. Do you want to add on something to this basis theorem? I still want to um, add some selling point for this basis theorem here. Okay, why is it useful? I want to add some selling point. Okay, I want to market this theorem here. So, in general, okay, for a vector space, you find basis. Okay, you want to use linearly independent and span, okay? Only these two you can get a basis of the vector space, and then with dimension f. Right? Every time I say if you want to show it's a basis, check linearly independent, check basis. Okay, but so let's change this color. Okay, but let's say the game changed now. Okay, how to change the game? So let me make it smaller a bit. This size. Let me. So let's. What if first you start with dimension n? Okay. Then how to get a basis? You can still check linearly independent or span, but now you can pick either one. Check one of them is enough. Okay. By this theorem here, you check one of them is enough. Okay. Either you check n of them is linearly independent, or you check n of them span B. So reduce the work of checking both linearly independent and span. Okay. So this is this part is how should I print it? But so on this side is what this side is what you deduce. Use, and then this side is what you know. So through this basis theorem, right? If you happen to know what's the dimension of your vector space, then you just need to check linearly or independent or span, then you can deduce, you get a basis. You don't need to check both. Okay, typically you need to check both, but let's say you know the dimension of your vector space, then check one is enough by this theorem. Okay, this is the key point of this theorem. Okay, there's no useless theorem that we will introduce if there's nothing use. Okay. Next is this one. Okay. So let's see if our change of basis matrix is different. So how to change, how to find. So how to find if we don't tell you the relationship between B and C. Okay. So how to find this? So like just now, what we did is we need to express the vectors in B and C first to find the change of coordinate matrix. So what's this question asking about? This question is asking about change of basis matrix from B to C. Okay, now you need to express B in terms of C. Okay. So let's write down what we want first, and then we will figure out how we continue. Maybe this is better. Use red. Okay, use red. Okay, so what we want, so in maths, right, we are very very target oriented. Okay, so you need to know what you want to know. So change of basis matrix from B to C. So let's write down B to C. Okay, from B to C. So by the theorem, what is B to C? You need to express everything in B in terms of C. So this is what you need to compute. Right? Make sense? Make sense? Okay. So you need to express everything in B in terms of C. So this is the coordinate vector. Okay. So what is B1 in terms of C? Okay. So let's write it down. Let's write. Suppose B1 of C is the coordinate vector x1, x2, and then B2 as y1, y2. Okay, all right. But there's no space here. Let us remove. Okay. Okay, let's start here. Okay, so we start here. Okay, so what do we have now? Okay, suppose this. Okay, and then what does this imply? So this implies that B1 is actually x1 times what? This is the coordinate vector in C. So these are the coefficient for C1 and C2. Up to here, anything, anyone has objection? Any objection? No objection. So far, okay. So far, okay. 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 So, what you're really doing is you can make this into a matrix multiplication. B1, and then matrix multiplication, matrix equation. Okay, this is just a first week content, right? You multiply a matrix with a vector. It's just using the column vector multiplication. Okay, so you need to solve these two. So you want to solve these two. Actually, there's a very convenient way to do it. Okay, we will extend our augmented matrix. So normally we will do like this, right? You will see that normally we might do something like this. Right? Solve the augmented matrix. Correct? Okay. But in the end, when you solve it, what do you get? You get a row reduced echelon form, which is the identity matrix, because you want to solve it. Okay. So instead of solving one by one, okay, you can solve it together. You can solve it together. Yeah. Actually, this is not the first time you see it. This is what you did yesterday when you put A and the identity matrix. Okay. Actually, you are solving 3 matrix equation there. Or I mean n equation there. You remember? So okay, let me show you yesterday. So yesterday you are asked to find n inverse, right? Something like this. Right. Okay. So you solve it as a 3 by 3 case. So let's say we put a 3 by 3 case here. So E1, E2, and E3. Right. So what you are doing is actually you are solving this y and then this guy and then this guy together. Okay. Yeah. Actually, you are solving n matrix equation together. Okay, so yeah. So it's quite surprising, but it is doable. Okay. So far, okay. So we can solve it in a big augmented matrix and solve it together in a big augmented matrix. Okay, so how to do this? So let us put the C1, C2 back. C1 is 1 minus 4, C2 is 3 minus 5. B1 is minus 9, 1, minus 5, minus 1 for B2. Okay, so I'll let you try. 2 minutes, solve for me. I want you to tell me the matrix later. Yeah, so the difference of this big augmented matrix compared to the inverse one is the right-hand side is no longer identity matrix anymore. Ready? Someone ready? I got the answer today, so don't worry. I can check now. So what's the result? Okay, so first you have to have the identity matrix so that you can solve it. Otherwise, you will have infinitely many. It's okay, but today we want the definite answer. So you got 0, 1, 0, 0, 1. So what's the right hand side you got? 6. Huh? 6 what? And then 4 row, huh? Okay. -5. -3. Good. Okay. So how do you read this result here? So let me make this smaller size. Okay, so how you read this result here? So this means that what? This means that x1, x2, x1 equals to 6, x2 equals to -5, y1 equals to 4, y2 equals to -3. Okay, which means B1 in terms of C is 6 minus 5, and then B2 in terms of C is 4 minus. Okay, So if you put this together in your change of basis matrix, the matrix you will get is 6 minus 5, 4, and minus 3. Okay. All right. Everyone follow? Okay. Follow? No question? Questions? Okay. Straightforward enough. Okay. All right. So next part is find the change of matrix from C to B. From B to C, sorry. So just now we from B to C, now from C to B. Okay. So how would you do? C to B. How would you do? Oh, inverse. Wow, very good. Yeah. The quickest way is to use inverse since you already have B to C. So C to B is just wait. C to B is just inverse of B to C. Okay. Of course, if you want, you can go through this torture again and then get C to B. But you can just take the inverse. All right. Okay. So you need to remember this inverse always exists because the columns are linearly independent because you started with basis elements. Okay. Otherwise, you cannot simply take inverse of a square matrix. It might not exist. Okay, I think quite straightforward here. So what we have done here actually is this theorem here. Okay, this theorem says that if you have C1, C2, B1, B2, okay, two bases, then if you row reduce to identity on one side, the other side is actually B to C, okay, because you already chase all the C to the other side. So B has become C. Okay, of course, this one not limited to only two. So you can put 3, 4, 5, 6, 7, 8, n by n. Okay, so I'm not sure why this is a just 2 by 2 case in your note, but okay, in this case, since I make it bigger, so I can use, can I? Use this. So C1, C2, up to Cn. Okay, and then slash with B1, B2, up to Bn. Can these two end difference or not? Why? Why they cannot be different? Why? Why? You know why? I look. Who's it up? They are the basis of the same vector space. So the dimension cannot change. Okay. So they must have the same sample value. Okay. So this one is row reduced to identity on one side, n by n matrix. Then you already chase all the C to the other side. Then you get B equal to C. So similarly, if you want to get B C to B, what can you do? You know what can you do? If you want the other direction, you can chase the B to the other side. Okay. Yeah, right. Yeah, this is more like mathematics. You can do whatever you want. Within the gameplay, you can do it. Okay. So if you make identity on the one side, then this one will become C to B. Because you make everything in C in terms of B. What? Inverse, yeah, inverse. Yeah, inverse. Yeah. Yeah, you can think of it as an inverse. Yeah, you can think of it as an inverse. So like this. So let me see. So like this, and then go back to inverse to sorry. Okay, so this is just like just swap the position of what we have learned last time, right? There's nothing wrong with swapping the position. Okay. So you just swap. Okay, so B is what we established at first. So TC to B is just inverse of TB to C. So inverse will change the direction here. Okay, the inverse can be absorbed by the direction, which is kind of natural. Okay, inverse going back. So your matrix also go backward. Okay, so we finished chapter 4. Any question up to now? Chapter 4, vector space. Any question? Yeah, we finished chapter 4. So next quiz will be up to chapter 4. 3 and 4. Because 3, I think there's nothing much to learn there. Just some formula for determinant. But vector space should have some content. Okay. Yeah, determinant, nothing much to learn, just Cramer's rule, 2 by 2 matrix determinant, and then cofactor expansion. I think basically these 3. Yeah, if you can compute these 3, done. But there's some concept question that I can play around in vector space. Vector space, subspace, basis, number of bases. Okay. Okay. I'll see what's in the tutorial question and then see what I can play around with the proof question. I think I promise I won't make it too hard, but if it is hard, then I will tell you next week. I'll give you some. If not, then should be normal. Okay. It's only 10:40 now. How about we take a break and then we come back? 10:50 we come back for the next part.什么？附加题？什么附加题？哦，不需要了，太高分了，你们太高分了，好几个100分，天啊！我们要管制一下，没有水准啊，全部100分。接到，接到。啊，不会太难，不过一定难。你想很远的你。那你的问题还在吗？要不要哪一个问题？ 哦，这个，哦，整个是早上。还是超一点的。那一定变给你，对，是不一样。就是比如说，但是那些啊，它对一个有另外一个有面，就是他们的反应是习惯会变成 A。你我们就说，问神这个不是把一个基本上。他一定会需要对你的更什么转正需要能够这样不是 哦，我知道，我知道，我知道。OK，OK，就算在 rank A 里面，就算在 A 里，比如说你看，在这一步的时候，这三个你不会选，所以这叫做有变嘛？要变的些，它本身都变，这里面本身在大环大，如果你是在中间的，都非常好。在它最后面对它是，这是有定。包括 然后这样很顺手。Hello, testing. Okay. So next chapter is chapter 5, eigenvalues and eigenvectors. Okay, so what is it about eigenvectors here? So let's give you some motivation. So motivation is AV equals to lambda V, okay, where lambda is a scalar. So if you have the V, okay, what's the lambda V is? What's the lambda V? So you multiply your V with a scalar. So you scale the vector. So either the vectors, so this is a V. So after you scale the lambda V, so what happened? So either you make it longer or you make it shorter, right? Okay. This one make it bigger. But so lambda V scale the vectors. Okay. So we are interested in this kind of matrix. So remember, matrix correspond to a linear transformation. Okay. So in a geometric form, we want to see what vector gets scaled under this matrix or this linear transformation. So for example, one easy example of matrix, for example, 2, 0, 0, 2. Okay. This is a linear transformation from R2 to R2, right? Because I feed in an R2, multiply with this matrix, you give me an R2. Okay. So what this matrix is doing is you scale both direction with 2. Okay. So meaning inside the R2, okay, let me draw the R2. Let me draw this. So inside here, every vector become longer. Right? Okay. So in this case, we will say this is equal to 2 times x1. Okay. So we will say that ax equal to 2x uh, and x in R2. But let's say my matrix is not a scaling matrix. Okay, it's a shear matrix. Okay, remember what does this doing to the vectors? Okay, what is this doing to the vector? So I don't exactly scale it, but what I done to the vector is I change the x coordinate, 2x plus 1, 4. Okay, if you recall from the example we did for linear transformation, this is like going from a square to something slanted without changing the uh, coordinate. Okay, makes sense. Okay, so meaning you see, so here is let's give you a reference point, right? So here is 0, 1. Here become 1, 1, 1, 1. Okay, here become 1, 1. Okay. So you might wonder if there any vector gets scale. So in this case, right, 0, 1 is not scale. It's like get rotated. But any vector inside this plane here gets scale. Can you figure out what vector gets scale in this case? So is there a vector when you multiply, you get a number time back itself? Okay, you cannot tell me 0, 0, okay? Don't say 0, 0, because 0, 0, right? 0, 0 doesn't fit into this game, because if you put 0, 0, okay, no, put a warning. Don't put 0 here, because if you put 0, 0, I can put any lambda here. Okay, so only 0, 0. Okay. So what xy you put when you multiply by the matrix, you get some number time back itself. Any idea? Negative 1, 1. Let's try out. I'm not sure what is this. Okay, negative 1, 1. So it's a random picking. Negative 1, 1. What do you get? You get 2 plus 2 plus 1 and 1, which is minus 1, 1. Oh, okay. Yeah. Okay. So this is what? This is equal to 1 times itself. Okay. So this means that under this transformation, negative 1, 1. Where's negative 1? Let me see. Negative 1, 1. This vector here stay the same inside this transformation. Uh, okay. So my original, my answer is 1, 0. 1, 0. 1, 0. What do you get? You get 2, 0. This is 2 times 1, 0. Okay. So if you look at another one, so if you look at, let me draw this one as a triple one. Or this one get longer. If you draw the other one, oh, this one stay the same, sorry. So this is minus 1, 1. If you do the other one, which is 1, 0, and let's say this is 1, 0, so it becomes 2, 0. Okay. Should I draw this? Yeah, draw this. So this one become longer. 2. Yeah. Some get stretched, some stay the same. Some get rotated. Okay. But we interested in those get stretched. Okay. For this eigen part. So what's the definition? So the definition is, let me get back to the definition. So the definition is a scalar is called an eigenvalue. So the scale factor is called an eigenvalue of a matrix if there is a non-trivial solution x such that ax equal to lambda x. Okay. And then that x, there's a name for it, it's called an eigenvector. Okay. Eigenvector corresponding to the eigenvalue. Okay. So far, okay? Yeah. Okay, so let me see what's the next. Next. So let's look at this. So let A be a matrix 1, 6, 5, 2, and then U as 6 minus 5, and V equals to 3 minus 2. are U and V eigenvectors of A? So this means that does there exist a lambda? There exists a lambda such that A U equal to lambda UV and AV equals to lambda V. Okay, so maybe we put two lambda then different lambda for them. Lambda 1, lambda 2, such that lambda. Okay, how to find U and V? Okay, so one way you can do it is, okay, let me show you one way. So one way you can do it is you multiply out the left-hand side and see what do you get. Okay. AU is 1562, and then U is 6 minus 5. Get for the matrix multiplication here. What do you get? What do you get? 6 minus 30, so you get minus 24. And then 6 times 30, 5, 30, 30 minus 10, you get 20. Okay. So is this a multiple of U? So is this a multiple of U? Yes. So what's the multiple? Oh, 6 times 5, which is negative 4 times. So how about AV? Okay, AV. So AV is 1652. V is 3 minus 2. Okay. So what's the matrix multiplication you get? 3 minus 12 you get negative 9, and then 15 minus 4 get 11. Okay. So is this a multiple of V? No, you cannot multiply to V, right? Because if you want to get 3 to minus 9, you need to multiply by minus 3. But minus 3 times minus 2 is 6. So it's not multiple of. But since we have come all the way here, right? What have we learned? Let's say we want to solve these two equations. As it here. Okay, so we've got a vector equation. Okay, can you come up with an augmented matrix? Hmm? Can you come up with an augmented matrix to solve U and V? Solving U and V, but can you relate back to what we learned? To solve U and V actually. Play around with the equation. Can you get a matrix equation out of this? Any idea? Any idea? So, so how about move it to the other side? Okay. So what is this? Can you factorize U? How? Multiply by identity matrix. Yep. So because you can see that this one is matrix, but this one is a scalar. So how you combine matrix and scalar? Okay, so you need a matrix to come into the game first. Okay. So to make matrix come into the games, you can put an identity matrix, which do nothing to the equation. Okay. So now you see you have a U vectors and then matrix. So now you can factorize it. So A minus lambda 1I times U equal to N times minus L2I times. Okay. So what's this? What's this? Matrix times vector equal to 0. Null space. Okay, null space, good. This is one of the keyword, null space. This is a homogeneous system. Right, homogeneous system to this matrix here, A minus lambda 1I. What is the null space? So U is in the null space of A minus lambda I, lambda 1 times I, and V is in the null space of lambda 2 times I. Okay, so the question changed into whether U is in the null of A minus lambda I times I, or V is in the null of A minus lambda 2 times I. Okay, then from here, you can use all the tools we learned from previous case. You want to determine whether it's a null. So just now we already found that U is in the null of A minus lambda I because it satisfies the equation, but V doesn't satisfy the equation for A minus lambda 2 times I, so it's not in the null space. Okay. Okay. So equivalent formulation of the same thing, same question. Okay, but we will come back to this again. So next part, that's the next part, next question. So we'll come back to this formulation again. So let's look at this question here. So let's have the same matrix again. Show that 7 is an eigenvalue of A, and then find the corresponding vector eigenvectors, right? Okay. So if you want to show that 7 is an eigenvalue of A, what does it mean? Okay. What does it mean? Okay, I need to add something to this definition actually. So what's the eigenvalue? What does this mean? For the scalar 7 to be an eigenvalue of A. What does this mean? Any idea? Yeah, just start with you. Any idea? What's the definition of eigenvalue? What's the definition of eigenvalue? There exists a vector such that AX equal to 7 times the vector, right? Okay, so let's see. So the scalar 7 is an eigenvalue value of A if and only if AX equal to 7x as a non-trivial solution. Okay, so but from what we learned just now, AX equal to 7x is equivalent to what? A minus 7i x times 0. Okay. So what is A minus 7i? 1652 minus 7 times 1001, okay, and x, which is equal to minus 6 minus 5 2 minus 7 minus 5, okay, x equals to 0. Okay, but what is this? I think this one is quite straightforward. This one quite straightforward. You see that this is a minus 6, 6, 5, minus 5. Okay, if this is, so let me, linearly independence. Okay, right? Good. Why? Why? Linear independent, yeah, why? Because you can take this as a minus of the other one, okay? Or if you row reduce this, okay, if you row reduce this, you will get 1, 0, and then 0, 0, right? Okay. Did I do something wrong? I think I did something wrong. This one. Okay. So if you don't know how to go quickly, you can go towards this step first. So you can go towards, you can scale everything first. Okay, if you scale everything, you'll get 1 minus 1, 0, and then 1 minus 1, 0. Okay, then you can add, subtract 1 from the other, and you get 1 minus 1, 0. Okay, so what does this mean? So this means that the solution to this homogeneous equation is, what is the parametric form? S1 equal to x2. x2 is 3. So it's equal to x2 times 1, 1. So, so what does this mean? So every vector in the form of x2 times 1, 1 is an solution or eigenvector solution. Wait, let me see. Solution to what? Solution. Okay, let me write out the solution part first. To the homogeneous system. Okay, system, which means it is a eigenvector corresponding. Okay. Let's see. Okay. Yeah, we already found the eigenvector also. Okay. Yeah, straightforward. Okay. Okay. Next. So what we've done is, if you consider the set of all solution A minus lambda I times x equals 0, is really the null space of the matrix A minus lambda I. We already talked about it. So this is a subspace This is a subspace. And it's called the eigenspace of A corresponding to lambda. I think we got a lot of time. So why is this a subspace? Why is this a subspace? So let me put the question down. So theorem. The null space of the matrix A minus lambda I is a subspace. Subspace of what? Subspace of what? You know where the vector space they live in? Subspace of what? Live in what vector space? Subspace of Rn, where n is the size of the matrix A. Okay, A is an n by n matrix, so size n. Because null space, you need to have A add on the vector, and then you get 0. Okay, so it has to be size n. Okay, got it. Okay, so what you should imagine is A is an n by n matrix, so you multiply on the n by 1 matrix. So how to show? Okay, I want to show this because I want you to get familiar with how to show something subspace. Okay, so subspace, the first thing you need to show that is the null space, the null of A minus lambda I is a subset of Rn. Okay. It is true because what? Because A minus lambda I is n by n matrix. Okay. So the n by n matrix add on a n by 1 matrix. And yeah. Okay. Okay. Secondly, is 0 inside the null space of A minus lambda I or not? Okay. That is A minus lambda I times 0 is equal to 0. Is this true? True. Not true. Someone said not true. A matrix multiply a 0 factor, do you get 0? Huh? You get 0? You get 0, right? Right? So there's which is true. Because matrix multiply use So how about second? So if for closed under vector addition, if u v in the null of a minus lambda I, okay, then u plus v is in the null of lambda I. Okay, so you need to verify this part here. U plus v is in the a null of a minus lambda I. So let's check what happens if you apply a minus lambda I to u plus v. Okay, right. So can you expand it out? So this is equivalent to a minus lambda I times u plus a minus. Okay, and then what do you get? What do you get? Since u and v are both in the null space of a minus lambda I, you get 0 plus 0 by assumption. This is the assumption. Okay. So it's in which is 0, 0 plus 0 is 0. So it satisfies the null space condition here. Okay. Next. And next, if u in null a minus lambda I c a scalar, then cu is in null. Okay, so if you don't remember the subspace definition, you have to remember accept now that you need to prove for this clause under vector addition. Okay, first of all is a subset condition, and then second of all is the zero vector condition, existence of zero vectors. And then third is closed under vector addition. Fourth is closed under scalar multiplication. Later, you can check back your definition of subspace, but let us show this. So you want to show Cu is in null A minus lambda A minus lambda times I, but you have the assumption that U is in the null space. So you need to check whether A minus lambda I times Cu is 0. Okay. So what's this? Okay. So we have to use matrix multiplication property to pull the scalar up. Okay. You can pull the scalar up all the way up from the matrix. Okay. And then so that you can add your matrix on your vectors. Okay, so this is by a linearity. Okay, let's say linearity of matrix multiplication. Really, one, you can check back your matrix multiplication section. Maybe we don't cover it, but we think that it should be obvious to see from the definition. So from this part here, you can see that the 2 multiplication here becomes 0, right? Because u is in the null space of a minus lambda. So c times the 0 vector, yesterday we proved that this is actually 0. So after all this, what do I want to say? What I want to say is So the eigenvector form a subspace. So meaning the eigenvectors for correspond to one eigenvalues, right? It's not just one vector. It's at least a subspace. So either a line or a plane is an infinite set. The infinite set. Right. Yeah. So it's an infinite set. It's either a line or a plane. It's a subspace. Okay. So actually, do you think it is weird? Okay, why weird? For example, R. Okay, can you count all the elements in there? Or not? Can you count all the elements in there? One by one. Can you list? Cannot, right? But I give you a basis. I say one. Everything create out of one. You just take your number times one, you'll get your number you want. The basis is one. Dimension is one. For example, R2. Okay, R2. Can you take all the point out? There are infinitely many points on the plane. But I tell you that I need two vectors. Okay, I just need these two vectors. Every point can be expressed using these two vectors. I call it basis. Right? So we try to reduce something infinite into something finite. Okay, this is what we're trying. But of course, we still have something with infinite dimensional. Okay, let's say our basis is infinitely many bases. Then in this case, linear algebra doesn't work anymore. So we need to try to find another tool to study this infinitely many things. Okay. Okay. So linear algebra is trying to turn an infinite stuff to some finite stuff that we can study and try to dig out every property that we want or we like or it has. Yeah. Okay. Okay. So how about go back to real life again? Okay. So go back to real life. So let's given this matrix A here. So it tells you that an eigenvalue of A is 2. Okay. So meaning there's vector such that ax equal to 2x. Okay. So now you want to find the eigenvalues, eigenspace. Eigenspace is the null space of A minus 2i. So you want to find the basis of it. So you want to find a basis of a null space. Is this familiar? Basis of a null space. Okay. I hope, let me see, do we have more times? Okay, let's spend 10 minutes. I let you try to do this. Okay, and then I need to run for toilet for a while. I'll come back. Is it going well? Know what to do? Anyone start row reducing already? Any progress on row reducing? You can discuss with your friend if you want. Oh, so easy, this a minus 2y. Huh? Okay, so reduce a minus 2i x equals 0. So what do you get? What do you get? This row is 2 minus 1, 6. Okay. If you want to get to the to what? To the row reduced echelon form, you can write 1 minus 3. And then you want to find the solution to this homogeneous system, you write down the parametric form. I still realize that some of you still don't know how to write parametric vector form. So try to brush up your skill. Okay. So let's see. So from here you will get x1 equal to half x2 minus 3 x3. Okay. If you wonder why am I writing like this, it's because from this matrix, what you should get is x1 minus half x2 plus 3x3 equals 0. Okay. So in this case, we'll get x1 in terms of x2 and s3. So s2 is 3. So x2 is itself, x3 is itself. Okay. So if you write in terms of x2, you will get half 1, 0 plus x3 s3 0, 1. Right? Okay. So what's the basis of this eigenspace, null space? So a basis of the eigenspace is what? Is these two vectors. Okay, in the quiz, right? When you write basis, right, you don't put this set here. Okay. Okay, I don't penalize you for this time, but next time I will. So basis is a set. So it's a set of vectors which are linearly independent and span. So you need to put this as a basis. Okay. Some of you just say now A is these two vectors. Okay, what is now A? Now A is a set of linear combination of let me call A is a set of linear combination of column of your vector. Okay, it's not just two vectors there. It's a set of linear combination of the two vectors. So what you can write is one way. The other way you can write is so one way you can write is so eigenspace or now A minus 2i is the span of 1 half extra and extra. Okay. So one way you can say that this null space is a span of these two vectors. Okay. In the note, what you do, let me demonstrate to you. So you write is these two. Okay. So this is wrong. Okay, because this is wrong. This is wrong because now space is a set of linear combination of some vectors. Okay. Don't tell you the vector, but some vectors. Okay. So I write like this is okay because it's a linear combination of two vectors. Okay, it's a span of this. So I cannot write like this. Okay. Also, you in the test you also write a basis of now a minus 2i is also like these two. Okay. This is wrong. Okay, why is it wrong? Because basis is a set. Okay, it's a set. It's not an element. It's not a vector. Basis is a set. If you want to say vector, you will say basis vector. Okay. Basis is a set of vector because basis is a set of vector. So you need to write. So the correction is like this, or you can write it's a span. Okay. Okay. So make sure you know what space you are living in. Okay. So I'm not harsh on you because this is just a GE course. So slowly you take in information, slowly you change. Okay. This time I won't penalize you, but next time I will. Okay. Do we continue again? Yeah, just continue. First time I can finish what I prepared. Next. So what's next? Okay, we should end at this two theorem before we go to the next section. Okay, so let's have a theorem here. Theorem. Okay. The eigenvalues of a triangular matrix are the entries of its main diagonal. So let us understand what this is trying to do. This is telling us. So for example, if you have a triangular matrix, okay, we have encountered this before. Triangular matrix, either upper or lower, doesn't matter. Okay. Then the eigenvalue of this matrix is eigenvalue of the matrix of A are 1, 2, 3. Okay. So this should remind you or make you relate to something. Okay. Diagonal of matrices is what? The product of the diagonal entries you will get the determinant. Okay. So this is kind of a similar properties you have in finding eigenvalues and and determinant. Okay. So you see that there's some things captured by this triangular shape of the matrix. Okay. This property easily follow out some of the properties. Okay. Should we prove this? Maybe we don't prove this. Let me talk about next theorem, and then if we want to prove, then maybe we'll see next time. So next theorem is let's say you got eigenvectors with different eigenvalues okay, respectively. So they have to be different. They're with different eigenvalues respectively. Okay, for now, right? Actually, you should observe that we have examples. Where's the example? One matrix can have different eigenvalue. From the example I gave just now, so you see the example I gave just now for this one. Just now Dexter found an eigenvector with eigenvalue 1. I gave an eigenvector with an eigenvalue 2, but it's the same matrix. And also we have done in exercise that, let me see, is it correct? Okay, where's the exercise? Where's the exercise? Yeah, so you can see that this exercise here, you can see that this matrix, you have 4 minus 4 as your eigenvalues. 7 is also an eigenvalue. So you could have different eigenvalues for the same matrix. So the statement is like this. So if you have eigenvector with different eigenvalues of n by n matrices, you see matrix A, then the set of V1 up to Vr is actually linearly independent. So what does this mean? So this means this provide you a new source of finding basis. Okay, this provide you a new source of finding basis. So you're not going to find generally pick and choose basis, but you find this specific set of vector, eigenvector to become your basis. Okay, why is this important, right? So in physics, when they do experiment, right? So if when you perform an experiment on an object, okay, maybe the objects don't change, just the variable change. Number you get is different. Okay, so an operator add on an they call it an observables. Okay, when you add on an observables, then you get uh the same observables with different variables. Okay, you scale it something like this, and then these observables will form linearly independent set if they give the different eigenvalues, if they give the different variables out. Okay, but this thing is kind of important in physics because physics every time you measure is measuring the same thing but with different measures, different numbers. Right? Okay. Okay. Any question before break? Question? Any question? I think there's one interesting question from Zanzhou here. Zanzhou, can you state the basis one again before we break? Let's do a clinic session. What was the question again? Basis, can every basis row reduce to identity matrix? Then the basis one. Right, to identity matrix. To identity matrix. Okay. So okay. Okay. Does every basis, okay, and does every basis row equivalent equivalent to identity? Yeah, the question is, does every basis row equivalent to an identity matrix? Okay. Okay, maybe this is not a proper question yet. Does every basis of a subspace, any subspace, right, row equivalent to an identity matrix? Okay. If this was if this is not a G course, it's a proper course, this question probably will exist inside my quiz or exam. Okay. So does every basis of a subspace row equivalent to an identity matrix? Okay. So a subspace is of a vector space. Okay. The subspace have to live in some vector space. Okay. What do you think? So after this question, we can leave. So 11:50, we will break. What do you think? Does every basis of a subspace of a vector space row equivalent to an identity matrix? So basis consists of vectors, right? So how is it a matrix? So you need to consider the matrix that's made up with the column made up with the basis vector. So when is this row equivalent to an identity matrix? Any brave answer? Yes or no? Yes. Who say? Who say yes? Who say yes? So yeah. No? Oh, there. Why? Okay. So I can counter your answer. And you say yes. You say because basis vector are linearly independent, right? Okay. Independent. So it is row equivalent to an identity matrix. Okay. So let me teach you how to counter a person. So if you want to say no, okay, you need to give them an counter example. Okay. What's the counter example? So let's say my subspace, I take the H, my subspace is a span of easy. We don't want to row reduce again. We choose the easy one. 0, 0, 1 and 1, 0, 0. Okay. Like this, just like this. So they are linearly independent. Okay. But when you consider the matrix they form, this is not an identity matrix. Okay. Not any identity doesn't equal to any identity matrix. Right. So what's the issue here? What's the issue here? Huh? Then in that case, it's not row equivalent to identity also. Right. So what's the issue here? So the issue here, it is only true when the dimension of the subspace equal the dimension of the vector space it lives. Okay. So when the dimension of subspace equal to the dimension of the vector space, then the basis will be row equivalent to the identity matrix. Yeah. Yeah. That's all. Yeah. Yeah. Because n by n matrix identity matrix already fix your dimension of your subspace. What do you mean by equal? Yes. So when their dimension, when the subspace, the dimension of the subspace equal to the dimension of the vector space, that subspace is actually V itself. This is one of the exercises in your textbook. At the very back, I think 30, around 30 somewhere there. Number 30. Yeah. Yeah. If this, yeah. Right. That's right. You can prove it rigorously using the set equalities. So you need to show something is here is in here, something is here is in here. You can use. Yeah. We don't do it here because we don't learn the equality, so try not to put it in short. Since we already learned set equality. Yeah, so if the dimension of the subspace equal to the dimension of the vector space is itself is actually that subspace is actually the original vector space. Yeah. Okay. Thank you. See you next week. Hope you have a good weekend. Bye.